Oke. Apa kabar semua ini? Sehat? Your PKPB so far? Okay kah? Everyone at home? Enjoying your PKPB? Or you miss USM? Enjoy. Okay. All right. Miss USM. Okay. We have to learn. Okay, let me share the content of this class. That's with our lithography topic. Okay, can you see the slides now? Okay, good. Sorry. Okay, so we'll continue today to look at the each respective process in the 8 steps of our lithography process. So before this, we have learned that lithography printing process can be also classified as a CED process, which contains coating, exposure, and development. And this CED can be divided into smaller steps, and altogether there are steps to be able to finish the CED process. So let's have a look at each of these process. So the very first process in this uh, lithography is called vapor priming. So we've covered briefly when I explained about um, the schematic diagram before this. So what's happening during the priming process is we actually um, vaporizing the gas source or the precursor material into vapor form. Well, it can also be done by liquid form like what is shown on this slide, but typically it's vaporized from the liquid form into a vapor form. Okay, and then the vapor form will be coated onto the silicon. So whether or not silicon has the silicon dioxide on top of it. So it will then form a very thin glue layer before we spin our photoresist for the next processing. So what it does is it promotes good adhesion from the resist to the wafer, in which you're gonna see pattern collapse if you don't have sufficient HMDS or something's wrong with the process, or you don't have any HMDS at all on the wafer. So after the priming process, it'll be followed by a dehydration bake in a hot plate to make sure that the layer is and intact before we spin coating our photoresist. Okay. So next step will be the spin coating of photoresist. So what's going to happen is we're going to dispense a small amount of photoresist. On this slide, you can see that it's 5 ml. Well, it depends on the technology, but last time when I was working in Solterra, the volume used was 1 ml, And we even had a couple projects running on 0.8 ml. Okay, such a small volume of photoresist for each single dispense. So the resist dispense through the nozzle. So you can see in the illustration there in figure number 1, and then it's going to be spun. It's going to be spun at a very high speed in a couple of steps, which will be defined by the process recipe in the quota. So it may go up to 3,000, 4,000 RPM depending on the thickness that you want to get. Usually, if you go to higher RPM, so you're going to end up with lower thickness. So if you spin your resist at lower RPM, you're gonna end up with higher thickness. Okay, let me show you a very simple curve for this. My can you see my whiteboard now? Nampak whiteboard saya? I'll just slowly pin. This is your waveform. So it's your side on top. This is your silic, and then this is a very thin layer of oxide, for example. And then you have HMDS up there, but a very thin one. You don't see that. So assuming you have you're gonna spin coat this thick of photoresist. So I'll just write down as PR photoresist. So this photoresist, you will have some thickness. So say D. Okay. So to be able to spin the resist, we normally follow. Well, this is what I did last time when I was the equipment engineer for track system. So this one is D, say in micron maybe. So the thickness of your photoresist. So this one will be your speed, spinning speed RPM, revolution per minute. So if you spin your resist at a low speed, say 500 RPM, 1000 RPM is considered low for coating process. So usually you're going to end up with a very high thickness. Okay. If you go for middle speed, so say you go for 3000, so you're going to end up with slightly thinner photoresist thickness. So if you go for highest RPM, say 4000 or 5000, you're going to end up with next is this curve. Usually it's going to look something like that. Okay. So this is called spin curve, photoresist spin curve in lithography process. Spin curve. Okay. So each resist it has its own viscosity. Dia punya kepekatan. Kalau you pakai resist yang lebih pekat, more viscous, so you're going to end up with a higher spin curve. Okay, katalah ni you pakai viscosity A, then katalah you second time you spin coat at the very same 3 different speeds, so you're going to end up with something like this if resist B is thicker than resist A in terms of resist viscosity. So the more viscous it is, the higher it is on the spin curve. Okay, the position. On the other hand, if you spin photoresist at 3 different speeds as well, using low viscosity, for example, low viscosity photoresist, you're going to end up with something like this. So lepas you dah ada photoresist ni, you can come back in the future to this particular spin curve, and you can tell already which particular speed do you need for what specific thickness. So for example, if you need to develop a new technology which requires maybe thickness of, at this point, okay, using this resist. So that means, for example, this 1 micron, maybe too thick though. But for example, if you need to spin 1 micron resist on your silicon oxide there, say it's 1 micron. So to be able to get 1 micron, you need to spin at this speed x. Okay, speed x. So next time, if you need to use the very same resist for your next technology, for example, which requires maybe 0.5 micron or 500 nano, so that means that you just have to come back to the spin curve, provided the resist is exactly the same and viscosity is the same. So you just have to come back to this point and see, oh, 0.5 micron now, so what's the speed? You just have to go to the spin curve and see what's the speed required. Okay, then you can set that into your coating recipe and then run the spinning process at that particular speed, and then for sure you're going to get that thickness on your silicon dioxide. Okay, so that is called spin curve. So when I was in Silterra last time taking care of track, every time a new resist comes in, so I have to produce this spin curve for every single photoresist. When process engineers would like to use the spin curve, then they can just look at the parameters, thickness, the viscosity, and so on and so forth, and then they can just plug in the parameters into their coating recipe for that particular technology. Okay, so that's one of the job scopes for equipment engineer in photolithography. So I'll just go back to the slides. Okay, slow spin can be somewhere 500 nano, 500 RPM. It can ramp up to 3,000 to 5,000 depending on the capacity of your motor. So you can see here in the image here, you can see this is the vacuum chuck yang akan hold the resist, hold the wafer by the vacuum. So vacuum akan ada kat tengah ni. Vacuum will be here right in the center to hold the wafer at high speed. Okay, dia akan sucking just by one point punya suction. Then the motor will rotate at whatever speed you set in your coating recipe, and then the resist will be spun on the on the wafer to be able to deliver the required thickness. So at the same time, there'll be solvent evaporation as well. Bila you spin at a very high speed, you'll actually drive off solvent from the center to the edge of the wafer, and then eventually off the silicon completely. So that is coating process. So the photoresist coating is then followed by soft bake process. So you're gonna put your wafer into a hot plate, encapsulated in a chamber at temperature 90 to 100 degrees C for a couple seconds. In this case, it's 30 seconds. So the role of the soft bake process is to improve photoresist to wafer addition. So you already have the glue layer by HMDS. So then you spin the resist, but resist contains some water as well. So the water will be, part of the water was already driven off during the high spin process, but then you still have the residue of the moisture and everything in the resist, so it's not yet intact. So we then have to bake. Macam you bake the cake lah. You bake the cake, you'll make everything more solid. So does this process. So improve resist to wafer addition, promotes resist uniformity on the wafer. So you will actually uniform the formation of the resist on the wafer. Improve line width control during etching. So this one will only come later. So it's not seen yet because you don't have exposure process just yet. But whatever you have at your coating process will actually impact the quality of your critical dimension or line width, or in fact line edge roughness, or some other stuff related to the printing of metal lines, or of the lines, or the holes by your mask or by your reticle. So this process will also drive off most of the solvent in the resist. As I said just now, typical temperature is 90 to 100 degrees C for about 30 seconds. So then this process is followed by a cooling process in a cool plate. So now after this process, your coating is done. So the resist is already baked. So then it's already cooled down. Now it's ready for exposure process. So remember CED. So now the C is done. So now we're going to look into E, then D. Okay. So when you talk about exposure system, um, we've been seeing evolution of the exposure system from the moment of its introduction. So the first time it was contact and proximity printing system. To be able to do the printing, you have to really do the contact kind of printing, and it's called proximity printing because it's very near to the substrate. But then we have issues of defects and gap control because of the contact nature of the printing process. And then the exposure process evolved to one-to-one projection printing, where you use the mask. We started using the mask, but then the nature of the printing is one-to-one. So that means whatever you have on your reticle or on the mask, um, is going to be printed exactly of the same size on your substrate. So substrate here means the wafer. So if you have 1 micron on the mask, so you're going to have 1 micron exactly on your substrate as well. So maksudnya you tak boleh print down the size to smaller size because of the one-to-one nature. So if you have 2 microns, so you're going to have 2 micron on your substrate. If you have 5 micron on the mask, you're going to have 5 micron on the substrate. So it's one-to-one. Okay, then the exposure system evolved to a step and repeat projection printing is called stepper. So stepper ni dia guna projection optics. We're gonna see later on, but then the process is very slow. Okay, so then it further evolved into a scanning system, step and scan system, where we call it scanner. So the focus is a lot easier, and then you even have the privilege of reducing the size of your feature on the reticle to the substrate. So that means whatever you have on the reticle or the mask, previously kita panggil mask, tapi sekarang kita dah panggil reticle because of the evolution as well. You can actually print smaller features on the substrate. Okay, smaller features on the substrate. We're gonna see later on in the next slide. So the first one on the left is called contact printing. The second one is called proximity printing because it's still near to the surface, but it doesn't have any contact in nature. So the first one is contact one-to-one. Proximity is also one-to-one. And then the last one on the right is called projection printing 4 to 5 times reduction. So that means whatever you have on the mask will be scaled down 5 times or 4 times smaller on the substrate. So look at the table down there. If you talk about contact printing, so the nature is one-to-one. So whatever you have on the mask will be printed exactly on the substrate. So resolution is down to about 1 micron or so, typically used for research. Proximity printing is of one-to-one nature as well. The resolution is more or less similar to the contact printing. It's a low-cost process. Then the recent one is called projection printing. It is capable of printing down or scaling down the size of the feature on your reticle 4 to 5 times smaller on the substrate. So the capability is down to about it's not exactly 1 micron because it depends on the system. So if you talk about DUV, I line, G line, H line, I line, DUV, ARF immersion in water, EUV, they all have different details in terms of the resolution. Okay, we're gonna learn later on how do we then get the resolution of each system. So this is how it looks like more or less in a very simplified version. You have a light source up there. So if you talk about a DUV system, if you talk about a DUV system, UV light source is a very general punya term. Huh? So if you talk about deep UV. So the wavelength is 248 nano. So deep UV at 248 nanometer punya wavelength. So in that case, the DUV will be shooting from the top. So the deep UV at 248 is produced by krypton fluoride laser, excimer laser. Okay, whatever, krypton fluoride. So then you're gonna have your shutter. Then you're gonna have your optics there. Then eventually you're gonna have your projection lens before the sample, and then the most below is the wafer on stage. So you're gonna have your light source, and then you're gonna have your reticle, and then you're gonna have your projection optics or your lenses and everything, and eventually your sample or the substrate on the stage. And the stage can actually move in different directions: x, y, z, and theta. So you can move x, you can move y, you can move z, you can move theta as well. Okay. If you want to have a very clear picture of this, you can watch the YouTube videos that I've shared on Elon. So it will actually show you how the motion looks like during the scanning process. So you're gonna have both movements at the same time in different axes, right? You're gonna see a lot clearer. Then how low can we print? How low can we print is called resolution. Resolution is the smallest feature that your scanner or your exposure system can print. Okay, so for example, if you want to print this, so you are the this kind of setup. You have this kind of setup. So you have your illumination system up here, for example, UV. Then you have your reticle here. Reticle and mask ni sama. Tapi sekarang ni untuk the advanced system we call reticle. We don't call mask anymore. But essentially it's a mask. So it's gonna block the light in certain areas. It's gonna let the light to pass through in some other areas. Okay. Then you're gonna have your projection optics, your lenses and everything down here, and eventually your wafer on the stage. Okay, wafer on the stage. So what do we want to print? So you can print anything you like. Okay, anything you like. You can even print your name on if you have your name on the reticle. So for example, kalau you nak print Fazira, for example, then you should have Fazira on the reticle. Then the Fazira punya nama tu will be printed on your circuit patterns. Kalau kat hujung kau nak tulis nama you kan, whatever, you can do that. Well, okay. So in this case, we're not printing your name, Fazira. Okay. So we are printing this feature, for example, L-shape feature. You have to print L-shape. Gelap Fazira. So well, you may have your name as well if you own the system or you have the reticle. So you can have that L-shaped features, and then you can have the square brackets for cubes here. You can also print this. So you're gonna print that. You can scale it down into that kind of features. Okay. So the dimensions of line width and spaces must be equal. So whatever you have on your reticle will be printed exactly as they are on the substrate, but it will be scaled down accordingly to 4 to 5 times. So for example, if you have 200 nano on your reticle, then if you say you're doing 4 to 1 projection, then you're going to have like 50 nano on the substrate. Okay. But the line width and the space that you have between the features, okay, line width will be here, line width. So the space between the lines is here, 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 here. Those need to be maintained while having the printed features. Okay, if you have the printed features, the ratio of everything needs to be exactly the same as on the mask or on the reticle. Okay, so as feature sizes decrease, it's more difficult to separate features from each other. Yes, because if you're printing like 5 nano or 7 nano, and then you want them to be very close to each other as well, line to line, in order to be able to pack more transistors onto the same area, to be able to conform to Moore's law, as what we've discussed before. So you want to pack more, and then the features have to be crammed together, and when you print using optics, using lens and everything, small enough, at some point you won't be able to resolve the features. Maksudnya apa yang you print kalau dekat sangat tu, you might not be able to develop the feature. Macam kita belajar dalam development process tu, you might not be able to develop the features well between the features. Okay, so we're going to see later on what are the problems associated with lithography process. So assuming you have I line here 365 or DUV 1 and 3, DUV can also use 248. Okay, it can also be 1 and 3. You can also use water in the optic system. It's called ARF immersion lithography, where you have DI water in between to be able to be part of the optics. So we're going to see later on ARF immersion. So this NA is actually the numerical aperture of the lens dalam system scanner. So it's called numerical aperture. Numerical, let me put it down here. Numerical aperture, okay, NA of the lens in the scanner, okay. So numerical aperture is NA. So the typical range of NA is somewhere 0.3, 0.4, 0.5, 0.6, just like what you see here. So then the resolution is this. The resolution is this. So how do we calculate the resolution? Okay. Oh, resolution is on other page. Oh, here, sorry, I missed it. So resolution is given by K times lambda. K is the process factor of the system. Okay. NA is the numerical aperture, lambda is the exposure wavelength, right? So you then have to you then can calculate your resolution that you can print on the substrate. So resolution is one parameter, one important parameter. The other important parameter is called DOF, or depth of focus. So when you have optic system to do the printing, so you can actually control the depth of focus by manipulating few parameters in the system, the resist, the lens, the the wavelength and everything, the ambient. So so in this case, what it means in simple term, DOF is the range of focus that you can print with good resolution on the substrate. Macam you kalau you ada kamera kan, you pernah pakai kamera kan? Pernah pakai kamera yang SLR. Siapa ada SLR kat sini? Anyone? Fazira pernah ada kamera SLR? No. Siapa ada kamera SLR? You tell me, how do you focus? No money to buy, okay? So wait for next year when you get a job. Anyone is SLR or camera? You tak ada buat digital photography ke? Wedding pictures ke? Something. Kan kalau you pegang kamera, kalau phone sekarang kita tak nampak lah kan, because everything is well set and well you can manipulate as well. Kalau you ada SLR camera, then you can turn the tu kan, dia punya knob tu kan, to adjust the focus. So that is what it means in simple terms. The depth of focus refers to range of good focus that you need to have in order to print your features on the substrate with good resolution. Kalau you pusing sampai satu tahap tu, dia dah jadi lebih blur kan. Bila blur tu dah out of focus. So bila you pusing balik, dia dapat in focus or with good focus. So in focus tu sampai daripada sini sampai ke sini, pusing balik tu is called depth of focus dalam lithography. Okay, so that is what it means in simple terms. But when you talk about projection optics, printing lithography, bila you print, there are certain height in this direction, in Y direction, in this direction, that you have to be able to focus in order to produce features with good resolution. Kalau you are out of focus, then you punya feature will be sengit ke, it will not be exactly. You want to print like this, for example, you want to print like this. square shape with good resolution. So if you're out of focus, you might end up with something like that. Okay, out of focus. Sama, so dia punya konsep dia macam you tak ambil gambar lah basically, because litho is basically process ambil gambar or process of printing to be more accurate. It's just that you use light instead of use stencils or engraving or whatever. Okay, so depth of focus, so it can be calculated as well using this equation. So if you translate if you zoom this, you can see something like this. So you have lens up there, then you have your resist with certain thickness. So then your depth of focus has to be within the range of the thickness as well. Okay, kalau tidak nanti you will be out of focus. So that means when you do the spin coating of your resist, you need to know that the thickness and DOF will be highly correlated. Okay, so DOF you have to know beforehand. Then that has to be adjusted in the scanning process as well, in the exposure process. Okay, exposure system, contact proximity aligner system. This one old version. You can just look at this later on. Projection aligner system back in 1980s. It looks something like this. This one is nowhere near to what we have now. The old system. Step and repeat system, or we call it stepper. Okay, step and repeat is called stepper. Sekarang kita panggil step and scan. Step and scan is called scanner. Step and repeat is called stepper. Stepper is the older version of the exposure system. Current systems we call them scanners. Okay, scanner. Tak ada stepper dah. Okay, this is another representation of the stepper exposure field. This is how it looks like. But to be able to understand the exact movement of the stage and everything, you need to watch the video on YouTube. Okay, you can see more clearly. Exposure system. Semua juga. Scanner is much faster than the stepper, but then it comes at a much higher cost, right? So light sources for the exposure system and the line width that can be printed. So back in the 80s, it was on 436, so it can print down to 100 and 1.2 micron, more or less. So then back in late 90s, we started to have DUV system 248. So this one is I-line 365. 248 is DUV. 193 is DUV as well. Oh, and ARF. Sorry, ARF, not DUV, ARF. So ARF can print down to about this line width. But normally at this point, we normally go for EUV already. It's just that it's more expensive. Okay, reticle versus mask. Essentially, a reticle is a mask. Cumanya when we talk about the evolution of the mask, then mask ni kita selalunya guna for one-to-one system where there's no scaling down of the feature on the substrate. Okay, tapi reticle tu is actually a mask lah. So reticle ni is the modern version of the mask. So critical dimension, if you look at the reticle, so it can print down in 4-to-1 ratio or 5-to-1 ratio. So that means if you have if you're talking about 4-to-1, if you're having 200 nano on the reticle, so you're gonna be printing 50 nano on the substrate. Okay, optical reduction permits larger reticle dimension, easier to print, higher throughput, alignment, less defects, higher yield, better flatness if you talk about a reticle. Okay, so when you print more and more layers, so you're going to have tens of layers on your IC later on after you've completed everything. So when you talk about printing tens of layers or hundreds of layers onto the same area, so what is crucial is aligning your new layer to your previous layer. So what we're going to be doing is actually stacking up tens of layers or hundreds of layers onto the same area, onto the same region, in accurate, accurate setting. So this is called alignment. So alignment is essentially aligning your current printed layer to the previous layer. Okay, kita ada measurement ni. When you finish your printing process, we have a measurement or a characterization. We call it overlay. Overlay is a form of measurement. Overlay, where you actually measure the alignment of your current layer in comparison to the previous layer in X direction, in Y direction, and you're going to see how much offset do you have by incidence or on purpose. Okay, so basically you need to know the alignment and they have to be accurately aligned. Okay, overlay accuracy is a measure of alignment system's ability to overlay the reticle pattern onto the wafer pattern. So that means the reticle pattern too is you can imagine that as your current layer, and wafer pattern is what you already have on the wafer during the printing process. So that means that is the previous layer. So you want to print the new one onto the previous one so that you eventually have this on this, and this have to be aligned perfectly. Okay. Overlay budget describes the maximum relative displacement between a pattern layer and the previous layer. So overlay budget itu maksudnya how much error, how much tolerance do you have before you are misaligned. Okay, sebelum you misalign your current layer to the previous layer, you need to know how much overlay budget do you have. So this is actually controlled in SPC as well, statistical process control. So you're gonna see charts in the lithography process where you actually control the overlay, upper spec limit, lower spec limit, and that has to be within the allowed specifications. Okay, so in general, the overlay budget is about 1/3 of the critical dimension. Well, it's not blanket for all. It depends on the technology. It depends on the tolerance of each device. But the idea is that you have to align your current layer to the previous layer perfectly, or you have a very small budget, overlay budget, between your current layer and your previous layer. So just imagine if you have to print a technology node down to or sub 10 nanometer, where your features are very small and the separation between your lines are very small. So how do you then allow yourself to have your overlay budget to be, it has to be very strict then, okay? Because you need to print exactly on top to be able to stack the device well. Okay, so alignment is what you have to do during the exposure system. So this is the notch as what we've discussed before. So before you actually do the scanning process or the exposure process, the wafer has to be aligned at the home position. Then only the what we call the scanning process will take place. Okay, so just imagine if your alignment the notch alignment is not happening, so your notch might end up here, for example, end up here, and you will have your theta overlay off so much in comparison to the previous layers. Kalau you print satu single layer je, it's okay because it doesn't depend on anything, and you can print in any theta you like. Your notch can be anywhere, but the moment you print on tens of other previous layers, so they have to stack. Kalau tidak, dia akan jadi cacar merbah. Okay. So to be able to do the alignment, you need to have your alignment marks for your current layer to be printed. So we're gonna have macam kita punya alignment mark ni macam you punya reference lah, where should be this position, how much is it from the center, how much is it from the left, from the right, and that alignment mark has to be aligned perfectly to the previous layer. So usually when you run your scanner process, there'll be a step called GA, or global alignment. GA. So the scanner will actually find home position of the wafer, and then the wafer goes in, and then it will start to align doing global alignment. So that means it's going to look overall alignment at multiple spots across the wafer, and then if the global alignment passed, then only the scanning will start. So if your global alignment fails in the scanner, the scanning won't start. It will just say it failed. global alignment. Okay, this is one of the common errors in scanner in lithography process. You're gonna see a global alignment error, GA error they call it. So exposure is done. So the next process is called PEB, post-exposure bake, where you do the baking after the exposure. It's necessary to activate chemically amplified DUV resist. So dalam DUV punya proses, if you talk about DUV, kita pakai CA resist, DUV punya proses, we normally use CA resist, chemically amplified resist. Some call it CAR, chemically amplified resist. So what it does is there'll be an activation during the PEV process where the high temperature, 100 to 110, is used to catalyze reaction in the resist. Okay, there'll be generation of acid, and then acid will diffuse, and then will smoothen the line and everything. And these can also help to reduce the line roughness as well, line edge roughness. PEB is also required for conventional I-line resist in order to reduce standing wave. We're going to see standing wave later on. Generally, what it means is if you want to print something like this, feature like this, ini maksudnya punya resist yang you don't remove in this area. And this is the resist that you have removed. If you're printing something like this, it may not end up exactly like that. It will probably end up with something like this. We're gonna see later on why is it so. But this one is called standing wave effect. SW, standing wave, standing wave effect. So where you have sinusoidal wave on the wall of your feature, of your resist feature. So kalau you zoom this one in, you zoom this in, you're gonna see something like that along the wall. Okay, it's called standing wave effect. So we're gonna see that. So with the right PEB temperature and time, you're gonna have a privilege of smoothing the roughness on your resist wall, thereby reducing the standing wave effect. Okay, so we're gonna see in the part 2 of lithography how is what is standing wave, what produces standing wave, and how do we solve the problem. Right, so we are now done with C, we're now done with E, now we're going into D, developments, code exposure and development. So now, remember, so you have already exposed the certain areas on your resist, and you have blocked certain areas on your resist from exposure. So as I said before this, bila you dah expose, you're going to have latent image within the resist. You tak nampak lagi feature tu, but then it's already there, embedded in the resist due to the reaction during exposure. Okay, so what it does now is we're going to develop the structure. So firstly, you have that photoresist on your silicon. Photoresist. So below you dah expose, then you're going to have something like that, latent image, but it's still there. It's not yet visible, tapi dia dah ada because you have already exposed certain area and blocked some other areas. And then the moment you develop, you're going to be left with features. Something like that. So this is this. For example, so it depends on your positive or negative resist, how's your what you call dark field or clear field of your reticle. Okay, so you're now going to develop using alkaline solution. The common one is TIMA, tetramethyl ammonium hydroxide, 2.38% concentration. So the rest is DI water. Okay, so you're gonna dispense the TIMA on the resist, on the resist, on the exposed resist. Then it's gonna be spinning at some speed as well. Then the developer is gonna be distributed uniformly across the wafer, and then you're gonna develop your features as intended. Okay, we're almost done. So let me see how many more, whether I can finish. Yeah, I think I can finish it in this class. Okay, apa masalahnya after kita develop? This is only one problem. We're gonna see more problems in part 2 of lithography, what are the issues around lithography process. But the issues of development is this one, the obvious one. Okay, so you want to develop something like this. You want to develop feature like this. Feature yang tadi square shape saya draw tadi tu. So you want to have something like that. But, well, ideally you want to have something perfectly square shape, ideally. But typically what we have is something like this. Is considered correct already, even though the profile is slightly positive. So we call it positive. Kalau you nampak trapezium macam ni, well, it's not like that. It's just slightly open at the bottom, slightly wider at the bottom. It's called positive profile. Okay, positive profile. You want to have something like this. It's not so expanded at the bottom. Positive profile, like that. If you don't develop your resist well, or your exposure Sorry, I was disconnected just now. Can you now see me? Had a problem just now. Sorry for that. Okay. Sorry, I was disconnected just now. Let me finish few more slides. Line problem, eh? Okay, hold on. Okay, can you see the slide now? Okay, good. So let me finish few more. Okay, after development, the process is called hard bake. Sebab kita develop tadi, remember we have 2.38% of timah and the remaining is DI water. So it's a lot of solvent in there. To bake the substrate in order to form better formation of the feature after the development process. So what it does is it evaporates remaining solvent, improve resist to wafer addition. Yep. So the baking is done at 120 to 140 degrees, higher than soft bake. So it's a post-developed baking process. It hardens the resist. So now you already have your features formed on the substrate. So we now want to harden the features. Okay. So remove solvent, prepares resist for subsequent processing, and and resist hardening as well. And the final step, the step number 8 in the 8 steps process is called develop, inspect, or we call it VI step, visual inspection, where you send the the completed or the pattern wafers under the microscope to check whether you have printed the correct circuits, and the formation is okay. There's no residue. Everything can be checked under the microscope to find defects, to prevent scrap, so on and so forth. Right, the final one is called a rework process. Rework process is actually a privilege for lithography process. What it means is if your 8 steps is wrong, kalau you ada satu silap dalam punya 8 steps of lithography process, you can actually strip the resist that you have printed on the substrate. So maksudnya kalau you dah end up with features like that on the oxide on the substrate, you can actually strip the whole resist area yang ada feature tu from the substrate and redo the process over again. Okay, so it's called rework process. So you can see from this illustration. So we have priming, spin coat, baking, blah blah blah, and then you finish the development spec. So under the microscope, under the visual inspection, you found out that, oh, there's some problem with our exposure process. So maybe, I don't know, the line is not small enough as on the spec, or you have defects, or you have resist coming, or you have underdeveloped or overdeveloped, or you have something weird, see defects, then you have a privilege of reworking the wafer. It means you strip off the resist, and then it will go back to the first step in lithography, and then it will be repeating the exact CED process, and then verified again at the VI step after the process. So this is not available for other processes in the wafer fab. There's no rework for other steps, other process steps. Okay, only lithography has this privilege. So even then, it's not privilege per se. It's a privilege in the sense that you can remove and redo the CED process, but it's being monitored. So the number of reworks are being monitored by the management. So you need to minimize your reworks in order to look good in terms of your lithography operation. Okay, so we're now done with part 1 of lithography. Any question would you like to ask? Can you follow so far? Okay, do you have any questions on lithography part 1? We're going to see problems associated with lithography process in part 2. So I'm going to upload the lecture notes later on. Ada soalan? Is everything okay? All right, good. Ada soalan, eh? So tak ada soalan, then today is what? Today is Thursday, right? Okay, then I'll see you tomorrow 11, isn't it? Tomorrow 11. So we're gonna go through litho part 2. Okay, no question. That's it for today. Thank you very much. Assalamualaikum and take care. Stay safe. Have a nice day. You too, Faika.